Why is defining extensive properties system boundary so hard? Imagine trying to draw a line around a cloud or a splash of water and saying, "This is my system." It sounds simple, but in thermodynamics, figuring out exactly where that line should go can be quite tricky. That's because extensive properties like mass, volume, energy, and entropy depend directly on how much stuff you include inside that boundary. If you move the line a little, the total amount of matter or energy inside changes. So, the boundary you choose really matters. Now think about the boundary itself. Sometimes it's a real wall or container, and other times it's just an imaginary line drawn on paper. The boundary might stay still or move around, especially if the system is open or closed. In an open system, matter can flow in or out, which makes it even harder to pin down the exact boundary. For example, in a chemical reactor, gases and liquids are constantly entering and leaving, so where do you draw the line? Plus, many systems are not simple. They can have smaller parts or layers, like different chemicals mixing or biological cells interacting. This makes it tough to decide where one system ends and another begins. Sometimes the boundary is fuzzy or changes over time, especially in natural environments or complex machinery. Measuring these properties adds another layer of difficulty. To find out how much energy or mass is inside, you often have to do tests or calculations based on the system's state. But if the boundary is not well defined, your measurements can vary. Changing conditions or how you set the boundary can lead to different values, which makes consistent analysis hard. So, the main reason why defining the system boundary for extensive properties is so hard is because these properties depend on how much matter or energy you include. The boundary can be real or imaginary, fixed or moving, and systems are often complex or changing. This makes it tricky to get a clear, consistent picture of what's inside and what's outside. Understanding this helps in designing better experiments, analyzing engines, or managing chemical processes more accurately. When you choose the right boundary, you can better track how energy and matter flow and make smarter decisions in thermodynamics.